for Dario's talk. But just so we'll just take the opportunity of a couple of minutes worth of extra time and get going. We might be able to, or might need it for the Q&A session. So from here in the SOFIA Science Center, Dario Fadda will talk to us about the data reduction and analysis of the SOFIA FIFI-LS data. So Dario, please take it away.
Okay, I hope you can hear me clearly.
Yep, you're loud and clear.
Great. So yeah, so Jessica explained all these nice results, and it's very exciting results, and I will explain the kind of the basic stuff how to get these results. So we'll go through the essential steps of reduction, essentially, with FIFI-LS data, how to find this data, so in the archive, and how to reduce them, and finally how to analyze. What are the tools that you can find to actually treat this data, and how we obtained this analysis for the paper that Jessica was talking about. So let's start with the archive. So all the data of FIFI-LS and of course all the SOFIA data are now archived in the USRA archive that is done at IPAC, and it can be found at the URL that you find at the bottom of this page. So when you search for the data, you can specify different things. For instance, you can specify the object, as you can see there on the top line. You can specify the radius you search. Then you can put some instrument constraints or search for a specific instrument, in this case FIFI-LS, even for a specific configuration. So, and then put some constraints on the type of data you want. So you want to have raw data, you go on level 1. You want to have completely reduced data, you want in level 4, and then click on search. So if you do this, you'll find another page after a little bit, because it takes a while to load, and you see the AOR that have been observed. For instance, this is the object we were talking about, NGC 7331. You can find the way to see the coverage. So you see all these squares, that red squares that are on the galaxy. You see each one of them correspond to an AOR, so essentially an observation, and that is on the left panel. You can decide then to select some AORs and download them. Now, in this talk, I will talk about starting from the raw data, so the lowest level you can find in the archive, and going through the reduction and analyze them. And there are several reasons for that, and I will explain slowly as we go through. So for downloading the raw data, you have to specify the level 1 data, and you want to only get the object, so specify observation type object. Otherwise, you get some other engineering data, like the data relative to the atmosphere that's been taken during the observations. Another thing that you want to do is specify a radius which is slightly bigger than what you find, because these are large galaxies, so you want to have a bigger radius, because otherwise you go with the object center, the object coordinates, and some of these AOR are farther from the center of the galaxies. And then you can specify your FIFI-LS. In this case, we observed we are going to reduce only the C+ data, so we just select the spectral element red, which gives us the coverage between 150 and 200 micron. Once you do this, you are again presented with one screen which has a lot of AORs. Actually, you can go and search all the AORs which are relative to every single observation. And at this point, if they are all related to the same object, so you didn't pick other objects that are inside the same radius, you can just click the top square, that top box, where I put the first arrow, select all AORs, and prepare the download. When you prepare the download, you have another pop-up window. And in this pop-up window, you really don't, they usually ask you if you wanted PNGs. PNGs are essentially some images that are being produced to show at least what you get from a very, very superficial analysis of the spectral cubes. You want to skip them, so you can just unselect the PNG and start the download. This takes a while because there are many files. In this case, there were like kind of 170 files, I think. After a while, you can save this stuff on your disk. So just to see what happens, I use the one Unix command which is called tree to see how this data are organized. Is once you download the zip file, you can unzip it, and you'll see that this will zip in a data file, and you have this structure that is shown on the left of this screen. So you have data SOFIA FIFI-LS, which is the instrument, and then you have levels. So you have the first level 4, where you can find the reduced data, the completely reduced data. Of course, in this case, we just downloaded the raw data, so this will be completely empty directories. And then you find the series where the data have been observed. So in this case, the galaxy has been observed in 2 different series. So the cycle 7H and the cycle 8 in observation B. And for each of these series, you will find a different flight where this has been observed. So in the cycle 7, it's been observed in 3 different flights. You can see that the arrow pointing to the flights. So you have flight and the number of the flight, 632, 634, 640, and 681 in the cycle 8. Now, if I didn't put the entire tree because it's going forever, so now I'm going from, for instance, for one flight, which is the most complicated, the 640, and I redo the tree, and we see that there is many other directory. So for each one of these, we have a proc, which is the process data, and the raw, which is the raw data. Let's skip the process data because we are not interested in this, and let's go to the raw data. For the raw data, in this special case, you'll find the 2 releases, the release 2 and release 3. So this shows that even when we archive data, then we are going to do several releases because we add some information to the headers of each file that is being observed, which can be, for instance, adding the estimated water vapor during the observation, or correcting some header keyword that were corrupted, and so we can recover some files that otherwise is impossible to reduce. So in any of these releases, you'll find another tree, and finally, in the end one will be the data where you find the raw data. So this is completely, it's very complicated, but don't worry, because when you are going to when you come to get this stuff, you can use just find all the data and get a list of this data. Now, a word about the name of these files. So when you find this raw data, these have a long name and with a lot of numbers and stuff. So what does it mean? So there is some logic in this madness, of course. We'll see that, as I specified here, they start with a progressive number, which is the progressive number of the file that has been acquired during flight. And then we have the second part, which gave the time of the acquisition, UTC. Then observation number that depends on the type of the OR that's being used. Then we have the object name, which how the object has been named by the observer. And then we have the part of the observation. So in this case, Act 4, which is the AOR that has been produced for observing this observation. And finally, we have offsets because this data have been dethered, and so it's not a staring observation, but the camera has been moved around just to have a better sampling of the PSF. And the offsets are shown here. So in this case, we have 2 files that are being observed with the offset -2 and -5 in X and Y. Then we have the node. So these are chop node observations. So the node is AB in this case, and these are going to be added later. Then the channel, so in this case is LW, so long wavelength. The red channel is called like that. The blue channel is called SW, like short wavelength. And of course, it's a FITS file. So this is like the description. And remember, for every pointing, there is a new file that's being generated. So why we're going to do all these efforts, so starting from this raw data to go with a pipeline through the reduction and getting level 4 data at the end, when level 4 are already available. So there are several reasons for that. First of all, the data in the archive are not completely homogeneous, so they have been reduced several times in different times, and the pipeline during this time advanced, and the calibration also changed. So you can find data being done for a flight in one way, and for the next series they are done in a different way. So the things are not completely homogeneous. Then the data are reduced for every single flight. So you can find this particular pointer reduced, but it's not being combined with the data from the previous series. So if you want to obtain the complete map of the galaxy, for instance, in this case of NGC 7331, you want to reduce them in a homogeneous way and putting them together in a final spectral cube. And then if you are particularly inside the data reduction, you can find some data that are a little bit not standard. So they have, for instance, a very high signal to noise, very high noise. And so you want to perhaps reobtain a cube by discarding some files which are very, very noisy. So in this case, you can obtain a better result. Finally, the pipeline at the end has a step to obtain the spectral cube, and this spectral cube is obtained by resampling the data in different positions. And to do this, you need a smoothing parameter. So what is done usually using a kernel that sample data with some weight from the center of each pixel. And so you can, depending on the kernel size you use, you can have more smoothed data or more picked data. So if you have a lot of point sources, you don't want to over smooth the data. I will show you an example later. So all this said, okay, you'll be probably interested at this point to install the pipeline. So here I give a lot of URLs where you can find the documentation. You can find all the repository of the in the GitHub where you can find the pipeline and how to install it. So here is my suggested way to install. Of course, you'll need to have an Anaconda Python installed on your computer, and then you'll proceed with the installation. So there is an environment file that you can download. I put the direct link so you can find it immediately. What you do is once you have the Anaconda Python installed on your computer, you create an environment, and using this environment YAML file that essentially specify all the packages that are needed with the version that are needed. So you are sure that this is going to work. Once you have the environment, you activate it and you clone the repository. And you finally do the installation in kind of developer mode, which is the pip install -e. And this has an advantage then every time there is a change in the pipeline, you can go into the repository, do a get pull, and you immediately have the new version working. And that's what I say here in the next file. So this is if you want to really be kosher, but if you really are in a hurry, there is also a Conda installation. So you can find in AstroPy there is a version of the pipeline, which is not the most up to date, but you can install it and try it out if you are lost with all these instructions. But anyway, the best installation is going through the Conda environment. Okay, so once you have the pipeline, you can have some troubles, you can find some bugs, you can find you can have some comments to do. If you want to make some suggestions, comments, or issues found, you can go on the GitHub. Of course, you will need an account on GitHub, which is very easy to obtain, and you can submit your issue. That's issues I put when the pipeline was released. The second step in installing the pipeline is getting the atmospheric model. So SOFIA, as you probably know, was a plane flying in the stratosphere. This means that it was flying over like 99% of the water vapor in the atmosphere, but still we have this 1% which is extremely disturbing. So we have a lot of telluric lines in the in the spectrum, and we have to model them to essentially kind of correct the data. And to do this, you have to take into account several things. So the altitude, the angle of observation, so the elevation in this case, and the precipitated water vapor that has been found in in this moment and this place where the data were acquired. And once you have this knowledge, you can try to find the best model, which is in this collection of ETRA models that we created. And this is what the pipeline actually is going to use. It's going to look into the header, find all the information, then select the best model to correct the information. So you need to get this library to actually run the pipeline correctly. And it's separated because it's pretty big, so you don't want to have too many things in one giant repository. So at this point, if you are okay, if you accept the black box, you can just run the pipeline and it'll be okay. If you are not okay, you're accepting black box, perhaps you want to have a look to your data in more detail, even to understand how they work. I will not go into this, but last year I produced a Jupyter notebook that can help you with this, and is still available in the SOFIA website. So I invite you to go through and check what I wrote to see actually how the data are acquired, how the ramps are appearing. So you can find everything in these raw files, and you can use this notebook just to go through and to have an inspiration to read these files. But I will talk more about running the pipeline and how to essentially configure all the parameters that are used in this pipeline. So the pipeline is organized in sequential modules, and each module has its own options. So you can save any steps, at any step, what has been produced by the pipeline, and so you can inspect if you want. And remember that in some cases there are steps that are done in multi-threading. So because most of our computer nowadays have multiple cores, so it's good to go faster. And so in this case, things actually in multi-threading are a little bit done kind of randomly, so you don't know exactly if it stops. It can give you some weird signal because it's not you don't know exactly where you are. So if everything goes well, it's perfect. If it doesn't, it could be a problem. But the pipeline could be run through a graphic interface unit, so a GUI, and this I will not explain because it's been very well explained in another presentation done last year by Melanie Merkel, who actually wrote the pipeline. And it can be still found here in this website. So I will skip this because I usually don't use the graphic interface. I'm kind of old school guy, and so I use the command line, and I'll show you how to do it. How to run it? If after installing the pipeline, you have to activate the environment. Otherwise, you cannot run the pipeline. So the first thing you have to do is activate your SOFIA Redux environment that you created when you installed the pipeline. The pipeline itself can be run with this simple command that I show here. So redux_pipe -c, which stands for configuration, redux parameter configuration. So this is the file where we are getting all the configuration parameters. And then the list of the files that you want to put together. So redux in files.txt. Why I'm doing this with no graphical interface? Because the graphical interface is pretty difficult to recover all the files. If you remember, we had the files in a very remote directory. So I prefer to get all the list of my files and use the command line. Okay, so how do I get my files? So usually what I do to be a little bit clear, so I showed you before that when you get the data and you unzip them, there is a directory called data has been created. So I just create another directory which is called reduced, and I go inside it, and here I do this command. So find dot dot dash data, and I search all the files. So this is the dash name, all the files which ends with lw.fits. So all the files that are being taken in the red channel that are in this data. So I know that I get them all, and I pipe them in the reducing files .txt, which is the list of my files. So once you have the list of the files, you need to act on your parameters. And that's what I'm going through now. So this is a kind of a long file which contains all the information you need for all the separate modules that are run by the pipeline. So the modules are clearly, in this case, sorry, they are clearly indicating green. And each of the parameters are in kind of this brownish color. And you can see very simply that there is a save, for instance, which means simply save this step, and which I put false most of the time because I don't want to conserve everything. Then there is kind of a intuitive a structure like parallel, one around parallel, essentially parallel multi-threading. You can do this multi-threaded if you do parallel true, so you go faster because you use all the cores of your computer. And then there are other specific information that you can change. So I will not comment in some specific information which are pretty standard. So for instance, in the fitting of the ramp, there are many things that you can change, like the signal, the threshold rejection. These are pretty well standard, so I advise not to change them. Then there are things like remove first, subtract bias. These are very technical, so I will not go even to explain this unless someone really wants to know it. Then there are, and this is essentially more descriptive, so I will not touch anything here. And there are a few things here that you can be interesting. So let's see, for instance, spatial calibrate. So in this case, you are essentially adding the astrometry. And you can choose to rotate your image, your final cube, to have a northeast orientation, or you can leave it, if in the case you get some data oriented in a particular angle, you can leave in this angle. So if you have data that are oriented in this particular angle, you don't want to make too much let's say resampling at the end that can create some fake structures at the border of the figures, and so you can put a rotate false, so you maintain the orientation of the array. In general, rotate true, it's okay. So in this case, it's okay because all the arrays are oriented slightly differently. Then yeah, there is nothing here that needs some explanation. Then we come to the telluric correct. So this is the phase where you apply these Etran models, and the Etran here you have to put in this case the position, essentially the path where you save this Etran stuff. So I didn't put anything because this depends on the choice, personal choice that you have. Then there's a cutoff. Cutoff is essentially I'm gonna consider just this is 0.6 in this case, which is very standard. So it means I'll consider valid all the value which has been essentially transmitted more than 0.6, so more than 60%. And I don't trust any data which has been absorbed too much, essentially. And you can use the use WV true. In this case, it's false because I don't know why I put it like that, but usually you have to put true because you wanna use the water vapor value that is in there in your headers, so which has been added to all the data that are now actually currently archived. Finally, you go through flux calibration. Here, of course, you don't have to do anything. And the correct wave shift is essentially applying the barycentric correction. So because, yeah, the Earth moves. And at this point, I put save through, and I will tell you later why. So I like to save this data because I want to do some checking later. Finally, we have the final step of the pipeline, which is the resampling, which is the one that essentially grab all the different observation and pack them in a cube, in a spectral cube. So which has, of course, X and Y. The first two dimensions are spatial. The third dimension is in wavelength. And here you have a lot of different things, and I will not comment too much. I will go directly to the spatial and spectral resampling. These are the most important one that you have to look. So you can check, you can choose the size of the spectra, the pixel that you want at the end, and this is the pixel size here. So in this case, I chose a pixel of 3 arcsecond. And then you can choose also which polynomial fit you want to interpolate. But the most important things are these things here. So this is the kernel that we are going to use. So these are in unit of FWHM, essentially the special PSF. So what you do here is choosing a kernel that is a Gaussian kernel, which has dispersion, which is in this case half of the FWHM, and expand up to two times the FWHM. So essentially, you are considering all the things that are around one single position of the pixel up to 2 FWHM with a dispersion of half FWHM. This is your smoothing, essentially, of the cube, because all the points you observe will be in very random places, also because of the dithering. Same thing applies to the spectral smoothing. The spectral smoothing is a little better because we have a lot of observation, a lot of oversampling. We do also a little bit of dithering in wavelength. So this is a less important things because there is a lot of redundancy. This is kind of more important. So once you have everything fixed, you can run the pipeline, as I said before, and we have a lot of products that comes out. So a note now about the resampling. So this is kind of a interesting point, I say, because what you get at the end depends a lot on how you smooth the sources. So you can have a very smooth cube, but you can lose a lot of information about the point sources. Or you can have a very choppy cube and recovering well the point sources. And this depends on how big is essentially the dispersion of the kernel that they are using with respect to the special PSF. And there is a way to do it with adaptive algorithm, which has been implemented in the pipeline, but it's not being really tested. So I will not talk about it so much. So just one word about oversmoothing. So now, in this case, this is an example of a galaxy, a joint galaxy that has been observed with FIFI-LS, and is a very picked edge. So you can see that when we go through and we check one of these pixels, we have a very nice pick in C++. So what happens here is that I put two different smoothing. So in the blue, in dark blue, I put the smoothing 0.5 that I suggested in the previous parameters, which conserve the spatial resolution, which means that more or less when you do the smoothing, you don't alter too much the FWHM of the spatial PSF. If you want to smooth more, so for instance, you put the smoothing parameter to 1, you're going to oversmooth. So you'll see immediately that when you go to the same peak, the peak will be depressed. You don't lose, of course, if you get a giant aperture, you'll not lose flux because the flux that you lose there will be somewhere else. But if you put a smaller aperture on the same spot, you'll have less flux. So this means that if you have a kind of point sources or very concentrated source, you are going to oversmooth. The oversmooth is going to depress these sources. So you can have fake results. So be aware of this. If you have places where you have point sources, you don't want to oversmooth. Okay, so this said, this is the list of the files that can be created by the pipeline. If you can click Save Through at every steps. And so I'm not going to read them. You have here the list. So, and everyone has a kind of identifier, which is these 3 letters. The only one I want to point to you is the 2 last one. So the WSH, which it stands for wave shift, and the WXY, which is your final sample cube. WXY stands for wavelength, X and Y, X and Y directions in sky. Each one has several extensions, and so I don't go into the detail here neither. But if you are accustomed to look at FITS file, you'll see that they have extension from position, from wavelength, from even correction of the atmosphere, and so on. Now the next step is, when you get this data, you want to have a look at them. So I created a few codes, if you want, that have a graphical interface, and that allows you to have a look to them and also do some analysis. And the 2 are suspects, and another one which I call cubic is in a bigger conda repository, which is called FIFI-LS, that I used also for calibration. So this is the way I suggest to install them. I just created new versions for Anaconda just for this school, so they are up to date with the latest version of Python and the latest version of Anaconda. So if you have any version of Anaconda you want, you can create an environment using Python 3.10, which is the one that is used nowadays. And essentially, as I did before with the SOFIA Redux, I activate this new environment. I install a few things that are needed. So these are codes for maximization, for reprojection, and FITS reading that are found in the distribution Anaconda Forge. And then you can go in my channel and install Suspect and FIFI-LS. So this takes a little bit while, but when you have it and you go in this directory, so you can actually run this code. So the first code I'm talking is the cubic code, which allows you to see where the different observations have been taken and how they are distributed along the spectral cube. So if you have your spectral cube that's in WXY file and your wavelength shift observation in the same directory, you can start cubic in this directory, and you get something like that once you open the file. So on the left, you'll see there are essentially the image of the galaxy, and all these little dots are corresponding to a frame. So if you know, a spatial pixel that observed the galaxy. So you see that in some cases there are more of them, and they correspond to the dither that has been done. In some cases there are less because we didn't have the time to complete the observation. Also on the top you can find the legend with the 4 different flights where the data were obtained. So you can have an idea how the observation has been done. You'll see that there is a little circle on the left panel, which essentially includes some of these pixels. We call pixel the spatial model, sorry. All these guys are shown on the right side. In the right side, you'll find that in this case, for instance, there are 3 flights that fall in the same circle. All these spatial models actually each one have 16 pixels. And so there are many points that correspond to one observation spatial in the spectral direction. So when you see this, you can see what we call the cloud of points that correspond to this spatial position. This is what the pipeline does: get this cloud and apply a kernel, which is a kernel in space and in wavelength at the same time, and does a smoothing of this data. So this gives you an idea of how the pipeline actually derived the cube and if there are specific problems. So in this case, you see that you can I'll show a little movie later. You can alter these two parameters. So this essentially the extension of the circle and also the extension of this segment that you see under the curve on the right to smooth more or less this data. You see a lot of data that's been circled with the black circle, and these are the outliers. So sometimes there are data that are completely off, so these are not considered in this case. And this is also a bit of a problem with the pipeline, because if you are too aggressive with the outlier, sometimes you cut the real signal. So the pipeline tried not to cut too many outliers. Okay, so here I have a little movie that shows how to write it, and it starts from my window where I have all this data, just writing cubic. When you do this, you start something, so you go in File, you open your cube. I have a filter in here, so I can find the WXY very easily. Then you write a moment, because in this moment it's reading all these files, tuck, and you have this. So as I told you, you can change the size of the circle, and you see the circle becomes big, and then you can move it, and you see how the data are appearing. Then I can change also the size of the essentially the kernel in the wavelength direction. I can move this so I can see what happens on the other side. And you can see that, yeah, as you move, you can see the different part of the ring in this galaxy, and also the thing. So the last thing I can do is, when I'm happy, I can compute a new cube. And so I essentially use my cube to compute a new cube. I don't advise to do this for a new cube, but the good thing of this is that the pipeline underestimates the errors, because I start from some hypothesis on the ramps. In this case, you can obtain another cube of errors that actually takes into consideration the dispersion of this cloud of points. So these are usually slightly better, more realistic errors. So what you can do is create a cube of errors and substitute this in the cube that you obtain with the pipeline. And now I have to go on, and let's go to the next step. So this is SOSPEX. This is another more complicated program that I did for analyzing the data. And yeah, here you have more information if you want to do a specific installation. If you want to go in the GitHub, there are a few tutorials that I wrote. And here also I have done two movies. One is just to show the kind of what you can do. So also in this case, you go in a directory where you have your spectral cube, and you start with the SOSPEX simply. And then you can select your files. So I do the same trick I did before. I grab my cube, and this shows immediately on the left the spatial distribution. On the right, you have an arrow that can navigate the spectrum. As you can see, as I move, you can see the different velocity of the ring. I can select my essentially my contrast. I can change from lambda to frequency. I can delete some of these lines that you can see. So there are a lot of interactive things that you can do here. If I'm not happy with the redshift that is there, I can move the line that I have to a line, and I can change the redshift. Or I can go directly to the redshift and change it there. So in this case, I'm not happy. Oh, no, I think it's different. Okay, I'll click, and the entire stuff moves. So I can also grab an image. There are many other things, but in this case, I saved the 160 micron image, and I can load it. And I'm not very happy with the level. So here we see our ring, and now I put some contour, and I actually add contour. In this case, I click on here, and I write I, so like insert. Then I can grab them. This is pretty difficult to get, and I can move them until I'm happy. Oh, now I see the ring, and I can go back and see where the ring is. And you see, I can go through the ring and get all my nice spectrum. Now, I'm curious about, let's get an aperture here. Okay, this is an aperture, circular aperture. I can change my radius here. I put 7.5, so I have kind of approximately the resolution of spatial resolution here. I decide to put a single Gaussian and the continuum. And here we have, yeah, perhaps you can adjust the continuum a little bit. Yeah, let's consider less. And now let's click and get my fate. And now I can, essentially you have a fate on this, which can be saved. So you can go through and say save, or just continue and redo it. Okay, so this is kind of a little demonstration how to do it. And now I think I'm going backward. Okay, this is the next movie, and I paused it because it started too much, sorry. So in this movie, I show how to get essentially a spectral kind of to fit the line all over the cube, and so get some parameters like the intensity, total intensity, or having the different momenta, like or velocity of whatever. So in this case, I can do a selection of regions. So I essentially put different points there. I have a Voronoi acceleration on the left, and I do my initial guess on one point. Then as I move, the galaxy actually at different velocities. So I have to adjust my guess. And you see, and when I'm happy, I can try to, I can put set medians, for instance, to get the continuum, and then I can run a fit in the specific region, so in this specific hexagon. And when I run this, the the program is running in parallel. It's getting me this fit. So this will be my my first guess, and at this point I can say my guesses and in a file, and then I can upload it tomorrow, the day after, and continue to work on it and refine whatever. And so this gives me a different panel for each one of the things I want to control in this line. So I will have, as you can see on the top left, I have I0, V0, and delta 0. So this is one line. If I have two lines, I will have I0 and I1. But in this case, I did a fit with one line. So I have the intensity of the line, the velocity of the line, and the dispersion of the line. I can save all this, and there is one possibility in the menu under I/O, which stands for input-output, which allows you to save all this extension with error. Okay, so this is what actually we did for the NGC 7331. So we used a very refined way to find all these initial conditions. So they see all the different Voronoi cells that I used, and for each of the one I adjusted it. So at the end, I have a map which is the intensity on the left, on the right, in the middle I have the SNR, so the pardon, the ratio between signal and noise, and on the right we have the velocity. So, of course, I cannot go through all of this, otherwise it will become a talk about SOSPEX, but SOSPEX I developed this for a long time, so now I can actually go through different cubes. In particular, if you have Herschel-Pax cube, you can use it. It's going to work exactly the same way. And I even read other instruments, because sometimes I want to compare two cubes, which is another possibility which I don't show. But I can get a spectral cube for one instrument, for instance, for one ALMA observation, and compare with FIFI or PAX. And so I can compare the two, go navigate with my pixel and see how the different lines appear. For the pipeline, I have a GitHub page, so you can submit issues, comments, and you can contact me directly if you have trouble to use this. I just released this new version because Python changed, and especially Matplotlib changed. Matplotlib has been released recently, and of course, as every a release on Matplotlib occurs, they break something, so I had to patch stuff, and it's not perfect yet. I have to find, I have to do more stuff. So I think I'm done. I don't know how I'm doing at the time.
You are fine, Dario. We have several minutes, and we have the
Perfect.
minute break if we need more. So, questions, please raise your hand or type in the chat for Dario. That was a lot of information here, Dario. Very useful. And as noted in the chat, Dario's slides are posted. So if you need to go and check something specific or get some detailed link, then they are available.
And of course, feel free to contact me if you have, if I skip some essential information, because I know I do it, I try to reproduce myself, but anyone starting to learn a new instrument finds some parts completely difficult, stumbles on many parts. So if you are doing this for the first time, please, and you have trouble, just send me an email and I will try to help you.
We
So
do have, I'm sorry, go on.
no, go ahead, Leslie. Your voice is better.
Yeah, we have a question in the chat from Anna. If you think about data calibration and reduction, what would you call the biggest difference between the ground-based and SOFIA data?
SOFIA is actually incredibly similar to ground data, in my opinion. It's not very, it's because the atmosphere is still there. Many people think that SOFIA data are like from space, like Herschel. But in reality, when you start doing them, you discover there are so many tellurics that you have to take into account. You have to take into account the atmosphere correction and so on. And we also have a limited calibration, unfortunately, because we couldn't spend too much time on calibration during the flights. And our best calibration, which was Mars, was not visible all the time. So our calibration is not super accurate. Let's say we are around, probably, depends on the wavelength, we are between 10 and 15% of inaccuracy, all things considered. But yeah, there are many challenges, as in ground observation. But of course, this observation cannot be done from the ground, so because far infrared.
Any other questions, comments, requests? So let me ask you, Dario, as a stand-in here, where would you, because we're reprocessing now, as you said, and you're also noted in your talk here that some of the pipeline processing as it exists is not maybe completely optimal. Where would you say are the data or the type of observations that you would particularly urge users to reprocess themselves with more direct parameter concern than what the pilot does?
We know that we are going to reprocess everything from cycle 5 to the latest data. And this will be essentially at the end of September, it will be released. And it will be processed with the latest calibration and the best way that we can do. Which means that all the data taken before are not reprocessed. So they are really old, so you better reprocess them if you need them. The other thing is, as I told before, there are data that have been taking several flights. If you want to combine them, you have to reprocess them. And the latest point is we do one fits all. So we get a resample parameter, which is used from planetary to the most distant galaxy observed, which can be not ideal, let's say, for people. So if you are a more diffuse emission, you want to reprocess with the kind of higher smoothing. If you are more pointed observation, you want to reprocess with the more pointed smoothing. So That's my advice. So it depends a little bit on your science case. We try to do the best, of course, the best compromise, let's say. So when you get something, you will get something which is hopefully close to the best, but it's not the best because we have to take sort of a medium way.
Can you think of any observation that are so, any type of observation that's so extreme, if you wish, that you would not advise people to use the pipeline? Is there any kind of...
There are a lot of point observation. I think more or less they are okay.
Okay.
Punctual objects. If you are observing something which is a mix, so you probably want even sometimes to use different parameters for different regions. Or you can trust the adaptive kernel, but it's not been. We have an adaptive line there, which I didn't talk about too much because we didn't have the time to test. It was just introduced, and we thought we were going to have more years, but we didn't. So that's one of the things that probably will stay there as experimental forever.
Good. Leslie?
We just have a comment in the chat about how informative your talk was, and thanking you for your very helpful presentation.
Thank you. And if someone really needs more help, I'm available.
I will second that comment, and thank you very much, Dario. And I think what we'll do now is we'll take a